Our last two units of the year are limits and derivatives. And in order to be successful in these units, we need to have a good memory of basic functions from Algebra 2. So what we're going to do today is revisit the family of functions that we learned in Algebra 2 to help us for future success in pre-calculus topics. What you'll see here are a couple of the functions that we learned about. First, you'll see our basic function, which we also call our constant function. And with a regular linear function, we have the equation y equals mx plus b, or f of x equals mx plus b, where m is our slope and b is our y-intercept. Recall that for any diagonal line, that the domain and the range are both negative infinity to infinity. Then you'll see over here I have a constant function. Now a constant function is when the y value stays the same, and it looks like a horizontal line. For a horizontal line, your domain is going to still be the negative infinity to infinity, but our range is just going to be whatever y value the line is at. So in this case, our range would just be 6. The next function that we learned about is the parabola or the cube graph. And in this case, we are taking our variable and squaring it. All right, so in this function, we have our variable being squared or cubed. And when you raise a variable to a power, it can have any x values, which is why the domain is negative infinity to infinity. Now for the parabola graph, if you recall this U-shaped graph, there's no negative values, which is why the range goes from 0 to infinity. Now if we flip the graph over, move it up or down, that's going to affect the range, but the basic range for parabola is 0 to infinity. With a cube graph, on the other hand, when you cube negative numbers, you also get negative numbers, so all values are possible. All right, I've also listed the domain and range for the absolute value graph as well as our square root and our cube root graph. These are all things that we learned back in Algebra 2, and the better you understand these functions and their general shapes, the easier it will be for you to understand how their graphs behave. Two functions that a lot of people forget about are exponential and our log or natural log graphs. So for our exponential graph, this one right here, there's an example of the graph f of x equals 2 to the x. Whenever we raise a number to a power, that number is never going to become negative. So we'll see here it gets exponentially big as the exponents get big. And if I were to use negative exponents, which is allowed, the number just becomes much smaller and it approaches 0. And we have a horizontal asymptote at 0, which is why we have an HA at y equals 0. This is why our range goes from 0 to infinity with a parenthesis instead of a bracket. With our log graph, log and exponential graphs are inverses of each other. And with our log graph, the domain is only positive values, so we cannot take the log or the natural log of a negative number. And in this case, we're going to see a vertical asymptote at x equals 0. The other three graphs that we learned about that we expect you to know are sine, cosine, and tangent, and we learned those earlier in the year, and I have those written down here. Okay, make sure you have all these values filled in, and then next we're going to talk about rational functions. Okay, when we're working with rational functions, these are any functions where the equation is a fraction, and we have variables in the denominator. Okay, when we're graphing rational functions, we need to find the vertical asymptotes and horizontal asymptotes. To find our vertical asymptotes, we have to set our denominator equal to 0 and then solve. There is allowed to be more than one vertical asymptote, and we write it as the form x equals a number. To find horizontal asymptotes, we need to compare the degree of the numerator to the degree of the denominator. If the degree of the numerator is less, then the horizontal asymptote is automatically y equals 0. If the degrees are equal, then we divide their lead coefficients, and if the degree of the numerator is greater, then we have an oblique or a diagonal asymptote. To find the intercepts, to get our x-intercept, we're going to set our numerator equal to 0 and solve for y, and then we'll write it as an ordered pair, a number, comma 0. To find our y-intercept, we plug in x equals 0, and our intercept will be of the form 0, comma number. We have encountered when a rational function has a point of discontinuity, and in order to find out when this happens, we want to reduce the problem and factor it. And when we factor it, whatever x value that gets crossed off that would have been a vertical asymptote is now a point of discontinuity, and it looks like a hole in the graph. And we'll see a few examples of problems like this on the next page. Another thing that we want to look up and refresh on is our unit circle. So fill in your quadrants and make sure you recognize all of your different ratios and revisit those if you need to. All right, next we're going to go ahead and we're going to take a look at how to do piecewise functions. Okay, when graphing piecewise functions, basically what happens is that we have a different function for each piece of the graph. So for this first piece where we see that we have 2x plus 3, this is a linear graph. This is like the graph y equals 2x plus 3. And this graph is going to occur for x values where x is less than -3. So if we look on our graph, that's going to happen for all of these x values this way. Okay? Since we just have a less than, we are going to have an open circle at that point. So what we do is we plug in -3 there. And when we plug in -3, we are going to get -6 plus 3, or just -3. So we get the value of -3, -3. So we go to -3, -3, and put an open circle. Now this line exists for all x values less than 3, -3. So then we're going to plug in a value less than -3, like -4. So -8 plus 3 gives us -5, which would be down here. And I can go ahead and connect the dots, and that is what that piece of graph would look like. If I look at it, it's a line, which I expect with a slope of 2. If I were to follow this graph all the way up and go up 2/1, I would see it crosses my y-intercept at 3. However, I don't want to do that because this graph doesn't exist all the way up there. The next piece of graph that I have is a parabola. For the parabola, I have x squared minus 4. Since both of these endpoints, the -3 and the 2, both are just less than symbols, they're going to be open circles. So I plug in -3, 9 minus 4 gives me 5, and I'm going to have at -3, 5. And -9 minus 4 is 5, -3, 5. Yeah, sorry, brain fart. Okay, and then now if I plug in -2, so we'll have 4 minus 4 is 0, so we'll have a point right here. And if I plug in -1, we'll have a point at -3. And then now that we can kind of see the U-shape of the parabola, we can think about where it goes until. So it's going to go until x values of 2. And we're going to have an open circle where it ends. And we can graph in that part of the parabola. All right. And then now for the last piece of graph that I have, it's just 6. And 6 is a constant. And since it's only a single x value of 2, that means it's just going to be the point 2, 6. I put a closed circle there. And that graph is done. Now what we're going to be studying in this chapter is how the graph behaves as we approach specific x values of the graph. And so it's important to be able to have a good visual of what our graph looks like. And that's why we are practicing the graphs today. All right, let's go ahead and take a look at the graph over here on the right. So here we have 4 regions of our graph. All right, so let's start with the first one, -3x. If we plug in -1, and some people prefer to make a t-chart for these. So you can plug in -1 and then other values that are less than -1. That's another strategy that some people like to do. And then we can just graph those points. Again, it's just less than, so we're going to have an open circle. And then my next one will be at -2, 6 and -3, 9. I'm just going to have this line right here. All right, now my next one is 2 to the x. So if I were to do a t-chart there, and plug in -1, 0, 1, and 2, and it sounds like I have grandkids, so I'll be back. Okay, so back at the graph here. All right, we've got, we're plugging -1 in, so that gives me 1/2. When I plug in 0, I get 1, 2, and 4. And we're going to have a solid circle here. And a solid circle here. So this little snippet like that. And then now we're going to have a constant piece from 2 to 5. So from 2 to 5, we're going to have a y value of 6, open circle here, closed circle here. And then the last piece of the graph is going to be an absolute value function. Now remember, absolute value functions look like a V. For this, I would recommend finding your vertex. So the vertex is going to be 7, 2. Since 7 is within this domain, we know that our vertex is going to be there. So we can go to 7, 2, and we can put a circle. And then this graph has a slope of 2. So I'm going to go up 2 over 1, up 2 over 1, and I only go as far left as, oh shoot, I did that too far over. Try that again. Okay, so the vertex is at 7, 2, right here. I'm going to go up 2 over 1, and I'm only going to go as far over to the 5, and I have to do an open circle. So this open circle actually goes over the filled-in circle, and then now I go the other way over to the 10, and then I can connect the dots to get my V. Notice that I'm not putting any arrows on these graphs because they are not continuing on forever. We want to make sure we clearly mark open circles and closed circles on our graph because that's going to be important when we talk about continuity. Okay, the next one you're going to try on your own. And the last thing that we're going to be reviewing today is rational functions. So graphs 5 and 6 are both rational functions. We know they're rational because they have a variable in the denominator. And in order to graph rational functions, we need to find those horizontal and vertical asymptotes. So our vertical asymptotes, this is any x values that make our denominators equal to 0. So if we look at this denominator right here, whenever x is 2 or negative 2, my denominator will be 0 or undefined. So I have vertical asymptotes at 2 and negative 2. And the way that those look on our graph is we draw them as vertical dotted lines. To find my horizontal asymptote, what I want to do is I want to compare the degree of the numerator and the denominator. Since the numerator has a degree smaller than the denominator, the numerator is a degree of 1, the denominator is a degree of 2, then that means that our horizontal asymptote is automatically at y equals 0. So I'm going to have an asymptote here at y equals 0. And these are kind of like the fences of the graph. The graph can occasionally cross the horizontal asymptote, but it's very rare. They're basically like the tendencies of what it follows. So now we go ahead and we find our x-intercept and y-intercepts. To find the y-intercept, you just always plug in 0 for x. So we'll have negative 1 over negative 4, or 1/4. So we'll have the point 0, 1/4, which is like right there. And then to find my x-intercept, I set my numerator equal to 0. So if I set my numerator equal to 0, then that gives me x equals 1, which means that at 1, 0 is when my graph crosses. And in this case, that actually means that this graph does cross our asymptote. Like I said, it is rare that it crosses it, but it does happen. And so now we go ahead and we fill in the rest. Now the graph is going to pretty much hug the curves of these asymptotes. And we can get the shape of the graph by plugging in different x values. And so if we test an x value, like let's say for example, we test the x value of negative 3 to see what it does on the left side of the graph, then I would have negative 4 over 5. And so if we plug that in, we would have negative 3 minus 1 over 9 minus 4. So negative 4 over 5, which we really don't have to be super accurate here. That's just enough to tell me it's going to be below. And so I know now that this graph is going to hug the asymptotes down there. And then if I plug in something on the right, like let's say I plugged in 3, then I could have, okay, I have 3 minus 1 over 9 minus 4. So I'm going to have 2 over 5, which is positive, which is enough to tell me that here my graph is going to be doing something like this. And that is essentially what we're going to need to know to be able to answer our questions about limits. All right, the rest is for you to fill in on your own. Have a good day.